Hi guys, I welcome you to my YouTube channel, Learn Physics with IBM. And this is my contact. Do not forget to share the videos. You can always contact me. You can always write a comment. I'm always willing to clarify anything you want. Do not forget we are dealing with solved past paper questions, and this is AS Physics, multiple choice questions, Physics 9702. And this is kinematics and dynamics. This is going to be part 8 of this series, and do not forget to download the documents in the video description. Just in case you are new to this YouTube channel, you can download the documents, print and follow through the videos for your reference. With time, you can always practice at your free time. Share the videos with your friends. So without wasting time, I want us to get started with part 8 of solved past paper questions so that we try to complete this. So in part 7, I think we stopped on this question here. That was on page 65. So in part 8, I want us to start from this question. So which quantities are conserved in an inelastic collision? Of course, in an inelastic collision, total energy is always conserved, total momentum is always conserved, but what distinguishes it from from elastic, is that kinetic energy is conserved for elastic but is not conserved for inelastic. So kinetic energy is not conserved, so we ignore A and B. For inelastic, kinetic energy is not conserved, but total energy is conserved and total momentum is conserved, so the answer here is automatically C. For all collisions, total energy is always conserved, although some of the kinetic energy may be converted into other forms, but the total energy remains the same. Linear momentum is always conserved in all collisions, but kinetic energy is not conserved for inelastic collision. On a planet, a vertically launched projectile takes 12.5 seconds to return to its starting position. The projectile gains a maximum height of 170 meters. The planet does not have an atmosphere. The planet does not have an atmosphere. That means it means acceleration due to gravity is constant, so the equations of motion can apply. If it doesn't have an atmosphere, air resistance is negligible. So what is the acceleration of free fall on this planet? So on a planet, a vertically launched projectile takes 12.5 seconds to return to its starting position. So I'll try to sketch this. So it is launched vertically. So it takes, going and coming back to the same position, the total time is 12.5 seconds. So it means the displacement is going to be 0 if it returns to the same position. So the displacement is supposed to be 0. But they're saying the projectile gains a maximum height of 170 meters. So going to the highest point and coming back, the height there, the distance there is 170 meters. That is 170 meters. So I'm just going to consider it falling from the highest point. Of course, before it returns from the highest point, velocity here will be 0. So now it starts falling downwards with increasing velocity. So I'll use, let me just consider it falling so that I can find the acceleration, because if I consider it going and coming back, I don't have the initial velocity. And let me first write the formula. S equals to ut plus a half at squared. If I consider it going upwards and coming back, displacement will be 0. I don't know the initial velocity, but I know the total time. Here I will be having two unknowns, so I will not use that equation. Let me consider it just falling from the highest point to the ground. So the time will be half. So the time of fall is going to be half of 12.5 divided by 2. That is coming from the top to where it started from. So the time, I think this is 6.25 seconds. That is the time. So that means Of course, the S is going to be 170. If it is just falling from the top, S is 170. Now I'm just going to substitute. So 170, it is falling through 170 is equal to initial velocity. Now it will be 0 if it is falling from the highest point where it momentarily came to rest. So initial velocity will be 0, so I'll just say equals to a half times the acceleration of free fall, then times time, which is going to be 6.25, and this is squared. So I'll just press my calculator to make G the subject. 170 times 2 divided by 6.25 squared. So this gives me 8.7. So the value of G on that planet is 8.7. So the answer is going to be B. A displacement time graph for a toy car is shown. Displacement against time is drawn here, which graph shows the variation with the time of the velocity against of the car. So remember, the gradient is the velocity. So here we have a constant gradient. So here the velocity is 0 because the gradient here is 0. The gradient here is 2 divided by 2, which is 1. The gradient here is negative. So 2 minus negative 2, that is 4. 4 divided by 1, so the gradient here is going to be 4. Then the gradient here is going to be 0. So velocity is initially 1. It's going to be initially 1, then 0, then 4 in the opposite direction. This is negative 4. The gradient here is negative 4 because I got 2 minus negative 2 divided by 1. That is 4. Then the gradient for a horizontal line is 0. So the answer is going to be A. Here velocity is 1, constant, because it is a straight line. Velocity goes to 0 because it is a horizontal line here on the displacement time graph. Then velocity goes to negative, is this negative 4? 2, sorry, this is 6 minus 2, this is 2. So this is negative 2, not negative 4. 6 minus 4, which is 2. The difference in time here, this time range is 2. So this goes to negative 2, and it is constant because it is a straight line. And this goes to 0 because it is a horizontal line. So the answer is A. A driver stops his car in time t by gradually increasing the total braking force on the car. Gradually increasing the total braking force on the car. The graph shows the resultant force on the car. Resultant force on the car. Which graph shows how the speed of the car will vary during this time? So remember from Newton's second law, force, resultant force is equal to mass times acceleration. So because it gradually increases the total braking force increases. That means the total acceleration increases, but this is going to be a deceleration. It is going to be negative. So the acceleration increases, but in opposite direction, or in opposite direction, but in opposite direction. So the acceleration is going to increase, but in opposite direction because it is braking. It is a braking force. It is actually going to be a deceleration. So since the acceleration increases in the opposite direction, it implies that the velocity decreases. So v decreases, or it should be slowing down. Okay. So it means if it is a speed time graph, the velocity should be decreasing, and all of them all show that the velocity was decreasing, and acceleration should be negative, but increasing. Remember, acceleration is the gradient. From a velocity time graph, acceleration is equal to the gradient. So the acceleration should be increasing but negative. So here acceleration is decreasing and negative. Here acceleration is negative but constant. Here acceleration is constant. So it means this is out. This is out. The acceleration should be increasing but in the opposite direction. So increasing and negative. Then C, the acceleration increases and then it decreases because the gradient first increases. Here the gradient is increasing and here the gradient is decreasing because the line is becoming horizontal. So here acceleration first increases, then it decreases. So it means this is also out. So it means the answer is going to be D, because here we see that the acceleration is just increasing. The graph is becoming steeper, so the acceleration is increasing. Also notice that the gradient is negative. The acceleration is increasing and it's negative, meaning the acceleration is increasing in the opposite direction because of braking. So the answer is D. The graph shows the variation of a quantity of a quantity y with a quantity x for a body that is falling in air at constant terminal velocity in a uniform gravitational field. At constant terminal velocity in a uniform gravitational field. Which quantity could x and y represent? Which quantity could x and y represent? Let's check. Let's do inspection. If x is air resistance and y is acceleration. X air resistance, y acceleration. If air resistance increases, the acceleration must decrease, so the line will become horizontal. So x, this is not going to be true, because if air resistance increases, acceleration with the time would tend to zero. So acceleration would tend to zero. Yet we don't see the line becoming we don't see the line going to zero. So that means this is not true. If x is air resistance and y is acceleration, it means the graph would be going down towards zero. Then loss of height. X is loss of height or decrease in height, and y is gain in kinetic energy. Y, loss of height, and y is gain in kinetic energy. Remember, the graph shows the variation of a quantity y with a quantity x for a body that is falling in air. The body is falling in air. So as the height decreases, if x is loss of height, as more height is lost, the kinetic energy would increase. But remember, it was falling at terminal velocity, so kinetic energy is going to be, the change in kinetic energy is zero. So since it was falling at constant velocity, the change in kinetic energy is zero, since V is constant. So that means the kinetic energy would remain constant. So this one is out. Since it is falling at terminal velocity, there is no change in kinetic energy because V is constant. So it means if Y was kinetic energy, it would be a horizontal line. Then C, I think C is going to be the answer. Loss of potential energy against work done and work done against air resistance. So I think this will be C. If we looked at loss in potential energy, it means the H decreases and work done against air resistance. So potential energy is mgh, and work done against air resistance, work done is going to be force times distance. So as more potential energy is lost, it means the speed. As more potential energy is lost, it means h decreases. It means the loss in h increases. More value of h is lost, And if more value of H is lost, the air resistance increases. It also means more work is done against air resistance. So the force due to air resistance increases. So the as more potential energy is lost, the loss in potential energy increases, air resistance is increasing. It means the work done against air resistance also increases, which gives us a straight line. So the answer is going to be C. X, time against velocity. Of course, this would be wrong. What would make this one wrong? If it was a graph of velocity on the y-axis against time, since it is terminal velocity, it is going to be a horizontal line. So this means D is wrong. At terminal velocity, it will be a horizontal line to show that the velocity is constant. So the answer is C. A ball of mass 2 kilograms travels horizontally with a speed of 4 meters per second. The ball collides with the wall and rebounds. This is very important. If it rebounds in the opposite direction, then one of the speeds must be negative. The time of the collision is 150 milliseconds. What is the average force exerted on the wall? So force, by definition, is the rate of change of momentum. So force is going to be, the change in momentum is mass into V minus U divided by T, or simply change in velocity. So this is going to be 2 into one of the velocities must be negative. So I'll say 4 minus negative 2.8 divided by the time, which is 150. Because it is milliseconds, I'll say times 10 power minus 3. So I'll press my calculator. So 2 into 4 plus 2.8 divided by 150 exponent minus 3. So this gives me 90.6 recurring, which is 91. So this is going to be 91. So the answer is D. An ice hockey puck of mass 150 grams moves with an initial speed of 2 meters per second along the surface of an ice rink. The puck slides a distance of 30 meters in a straight line before stopping. What is the average frictional force acting on the puck? So it moves with that initial speed along the surface of the ice rink. The puck slides a distance of 30 meters in a straight line before stopping. So it means it is losing kinetic energy, and the only force causing a loss in kinetic energy is the work done against is the frictional force. So it means the loss in kinetic energy should be equal to the work done against friction by the time it stops. So I'll simply say loss in kinetic energy is equal to the work done against friction. So the loss in kinetic energy is going to be a half m v squared. Of course, final velocity will be 0 when it comes to rest. And the work done against friction will be the frictional force times the distance it moves. So this is going to be a half times the mass, which is 150, times 10 power minus 3, then times the speed, which is 2 squared. This is going to be equal to, I multiply by minus 3 because the mass was given in grams. This is going to be equal to the force, which is required, times the distance it moves, which is 30 meters. So I'll just press my calculator. A half is 0.5 times 150 exponent minus 3 times 4, then divide by 30. So this is 0.01. So the answer is going to be F is going to be 0.01 newtons. So the answer is going to be A. Three forces acting on a hot air balloon that is moving vertically are weight, the force due to air resistance, and the upthrust. The hot air balloon descends vertically at a constant speed. That means the acceleration is equal to 0. The resultant force should be equal to 0. It is descending, moving downwards. So if motion is downwards, this is motion. the weight is downwards, it is descending downwards. Of course, the upthrust is always upwards, and that means the drag force is also, or the viscous drag is also going to be upwards. The force of air resistance, the force of air resistance on the balloon is F, so the viscous drag has been called F. Which weight of the material must be released from the balloon so that it ascends vertically at the same constant speed? Now we want it to ascend. It was descending, we want it to ascend. Okay, so if it was ascending, if it was descending, the weight or the force F plus the upthrust should be equal to the weight at a constant speed. So this is if it was ascending. If it was descending, for a constant speed, the force, viscous force F plus the upthrust should be equal to the weight. That is if it was descending. If it is to ascend, if it is ascending, remember the F will be acting downwards and the weight will be acting downwards. It is only the upthrust which will be upwards. So if it is to ascend, then F plus F if it is ascending, then F plus of course the weight must be reduced. So F plus the weight minus a certain value of force should be equal to the upthrust, because if it is ascending, the only force acting upwards is the upthrust. I don't have enough space here. Okay, let me sketch here. If it was ascending, it is going upwards, the weight is downwards, the upthrust is upwards, but this weight must be reduced by a certain quantity R, because the force due to air resistance F is also downwards and is constant. So F plus W minus R should be equal to the upthrust. So I have now two equations. I have this one and I have this one here. So I'm going to try and combine these two equations by adding them, maybe. So if I add the first equation, F plus upthrust equals to weight, that is when it was descending, to F plus W minus R equals to upthrust when it was ascending, then I should be able to get R. I want to find R. So I think, let me try to add these equations. So this is equation number 1, this is equation number 2, and I'm saying equation number 1 plus equation number 2. So I'm going to have F plus F, which is twice F, that is 2F. And of course, upthrust will cancel because it is on this side, it is on the left, the other side is on the right hand side, so it will cancel out. Then W will also cancel out because on here it is on the left. Okay, I know some of us may not be good at maths. Let me just add it physically. So I'm adding the two equations. So I have F plus U on the left hand side plus F into plus W minus R should be equal to W plus U. I added the left hand part of the equations and the right hand part of the equations. So let's cancel out what, of course, F plus F is 2F. U cancels out, W cancels out. So I have the 2F minus R equals to 0. So it means R is going to be equal to 2F. So R is equal to 2F. So the answer is going to be B. The question was which weight of the material must be released. So W must be reduced. That's why I said the weight should be W minus R if the upthrust force, if the viscous drag is F, and up thrust is still u, then W minus R plus F should give us up thrust if the speed is to remain constant. So R is going to be 2F. So the answer is B. A car is moving at a constant speed in a straight line with the engine providing a driving force equal to the resistive force F. Driving force is equal to the resistive force F. So that means the resultant force is 0. When the engine is switched off, the car is brought to rest in a distance of 100 meters by resistive force. Okay, so that means the acceleration is going to be negative. It may be assumed that F is constant during the deceleration. The process is then repeated for the same car with the same initial speed but with a constant resistive force of 0.800 F. So the deceleration is going to be changing. How far will the car travel while decelerating? So for the first case, the deceleration is going to be from Newton's second law of force equals to mass times acceleration. So the acceleration, which is going to be negative because it is coming to rest, negative F over m. Then using the equations of motion, I will have that we have that v squared equals to u squared plus 2as. So if it comes to rest, final velocity is 0. So I have that 0 squared equals to the initial velocity u squared. Because it is decelerating, the acceleration is negative. So I will say minus 2, where there is a, I will put f, divided by the mass m times the distance it moves is 100 meters. Then for the second case, let this be acceleration 1. For the second case, I'll call it A2. A2 will be now F changes, so it will be negative 0.8 F divided by M. That is the new acceleration. So again, substituting in the same formula, V squared equals U squared plus 2AS. I have that V squared is 0 squared since it comes to rest. Initial velocity, they said with the same initial velocity, so this is going to be U squared. Again, minus 2 into 0.8f over m times the distance it travels. I will call it just s times s. So I have two equations, and I'm just going to, since u is going to be the same, I'm just going to equate u squared, taking u squared on one side, u squared on one side. I'm just going to equate the two equations. So I'll simply say that 200f, this one gives us, this one means that u squared is equal to 200f over m. This one will also mean that u squared is equal to 2 times 0.8f over m times s. So I'll just equate the two equations, this one and this one here. So I have 200f divided by m is equal to 2 times 0.8f divided by m times s. So the only unknown here which is going to remain when we cancel out these different quantities. So f cancels, m cancels. So I remain with only s. So I will just check with my calculator. 200 divided by 2 times 0.8. So that is s is going to be 125. So s equals to 125 meters. So the answer is going to be B. So the answer is B. What is the statement of the principle of conservation of momentum? Of course, conservation of momentum, the momentum of an isolated system is always constant. An isolated system is one on which there is no resultant force acting. So here the answer is just D. A stone is projected vertically upwards from the ground at an initial speed of 15 meters per second. Air resistance is negative. What is the maximum height reached by the stone? So If acceleration air resistance is negligible, the acceleration is constant, so the Suvat equations can work. V squared equals to U squared plus 2AS. At maximum height, velocity is 0, so 0 squared equals to 15 squared. Since it is moving against gravity, acceleration will be equal to negative of g. So this will be minus 2 times g, which is 9.81 times s. So taking 15 squared on one side, I'll divide by 2 times 9.81. So this gives me 11.5. This is 11.47. So S is 11.47 or 11.5. So the answer is B. A hot air balloon is moving vertically upwards with a constant speed of 3 meters per second. A sandbag is dropped from the balloon. It takes 5 seconds for the sandbag to fall to the ground. What was the height of the balloon when the sandbag was released? Okay. So a hot air balloon is moving vertically upwards. I'll try to sketch this. It is moving vertically upwards with a constant speed of 3 meters per second. Let's say it starts from this level here and it moves with a speed upwards of 3 meters per second to the highest point. Remember here velocity is 0. A sandbag is dropped from the balloon. It takes 5 seconds for the sandbag to fall to the ground. So let's say the sandbag now falls when the other one was moving upwards. So let's say it falls through this distance. If it falls through this height here, h, and then it continues downwards through a distance x. So we need to first know the maximum height to the maximum distance upwards, or call it h. So I'll just consider maximum height. So to maximum height, I will use v squared equals to u squared plus 2as. At maximum height, v is 0. So I will have that 0 squared equals to initial velocity was 3 squared. Since it moves against gravity, I will say minus. Acceleration is going to be minus g. So a is equal to negative g. So this will be minus 2 times 9.81 times the height, which I'm calling h. So what is h? I'll just check with my calculator. 3 squared is 9 divided by 2 times 9.81. So this is 0.46. So h is 0.46 meters. So going up 0.46 meters, falling to the same level, it is 0.46 meters. That one cancels out. The question is, what was the height of the balloon when the sandbag was released? So a sandbag is dropped from the balloon and takes 5.0 seconds. Now we are going to consider this sandbag falling from the highest point to the ground. So if I use V equals to U plus AT, and T is the time to reach the maximum height, V equals to U plus AT, where the T I'm using here is T to maximum height. T to maximum, I'm using the time to reach the maximum height. What is that time? So the time to reach the maximum height, remember at maximum height V is 0, initial velocity is 3, so the time to reach maximum height is simply going to be 3 divided by 9.81. That is the time to reach the maximum height. So what time does it take to fall to the ground? Remember, the total time for all the motion is 5. So time from maximum height to the ground, t from maximum height to the ground. What will be that time from the maximum height to the ground? So this time is going to be equal to 5 minus 3 over 9.81. And what is this time? 5 minus 3 over 9.81. And that time is 4.7 seconds. So this time is equal to 4.7 seconds. So it takes 4.7 seconds to fall from the highest point to the ground. And just to fall the distance h, it takes, of course, the same time, which is 3 over 9.81. So we can now find total height. I can now find total height. So let me use this side now. Total height. I'm just considering it falling. So total height fallen through is going to be the distance. I said let it be x plus h, but h is 0.4, x plus 0.46, x plus 0.46 is the total height. Of course, I'm using s. Let me use s is equal to ut plus half at squared. I'm going to use s equals to ut plus a half at squared. Remember, u is going to be 0 because I'm considering it when it is falling from the maximum height. So s is going to be x plus h, which h we got 0.46. Should be equal to, it is falling, initial velocity is 0 from the highest point, is equal to a half times g 9.81, then times total time of fall is 4.7 squared. So I just find x. So a half is 0.5 times 9.81 times 4.7. It was squared, so I'll just multiply again by 4.7, divide minus, not divide by, minus 0.46. So I'm getting x as 107.9 or approximately 108. So x is equal to 108 meters. So what was the height of the balloon when the sandbag was released? So if the sandbag is released from here, the height of the balloon must be this distance x. So the answer is going to be automatically B. It was quite long, but it is worth it. The velocity time graph for a train starting at one station and stopping at the next station, the next is shown. Another train has a double the acceleration but the same maximum speed. Twice the acceleration, so the gradient is going to be steeper. Same maximum velocity, so it will be that. And the same deceleration, so it will be and the same deceleration. Another train has double the acceleration but the same maximum speed and the same deceleration. So okay, this is a repetition anyway. Which velocity time graph on the same scale shows the motion of this train between the same station? So if it is having double the acceleration, the gradient should be twice as steep. So which gradient here is twice as steep? So this is twice as steep, but the deceleration is wrong because the deceleration, let me check. So the answer is going to be B. The answer is automatically going to be B. If we want to easily verify this, because they said another train has double the acceleration but the same maximum speed, and the same deceleration. So let's say these are 8 small squares, and this is 4, and this is 9 small squares, and this is 11. So same area for displacements, so it should have the same area for displacement, because displacement is the area under the graph. So the displacement represented by this, if I just give them numbers, give the boxes numbers, the displacement will be a half, it is a trapezium, into 5, are they 5? 1, 2, 3, 4, 1, 2, 3, 4, 5. So this is 5, A is 5, plus B, which is 11, times 8, and that will be 64. So 64 squares, or 64 is representing the area under that graph. So they are saying which velocity time graph on the same scale shows the motion of this train, but between the same station. Because they are moving between the same stations, I say the displacement is the same. The displacement should be the same. So the area under these graphs should be the same. So I'm saying the answer is B, because me by inspection I see it is B, but let me check. These are 2 boxes, and 1, 2, 3, 4, 5, 6. So this will be 8, and this will be 10. This is 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. So let me check the area. Remember, the displacement is the same because it is between the same stations. The distance has not changed, the displacement has not changed. So S is going to be a half area of a trapezium. 1, 2, 3, 4, 5, 6. So that will be 6 plus 10. A plus B, a half A plus B times the height, which is 10. Times the height, which is 8. So let's check this one. That is 60 divided by 2. 16 divided by 2, which is 8, times 8, which is 64. So the answer is B. The area under the graph should be the same. If it is velocity time graph, the area is the displacement. Since they are both moving between the same stations, it means the distance they move is the same. So the area under the graph should be the same. You can try to check A, but it will not be correct. You can check B, you can check D. A stone is released from rest and falls a long distance in air. Which graph could show the variation with time t of the acceleration? Since it falls in air, the acceleration must decrease. Acceleration must decrease. So this one is showing the acceleration increases. This one is showing the acceleration is constant. And since it is in air, the decrease in acceleration will not be uniform, simply because the force due to air resistance is directly proportional to the square of the speed. So it means the acceleration, the acceleration cannot be, the graph of acceleration with the time cannot be a straight line, because this is not a straight line. So it is not a straight line. So that makes B wrong, because force due to air resistance is directly proportional to the velocity squared, and yet the acceleration decreases with increase in air resistance, and then yet the increase is directly proportional to the square of the speed, so it will not be a straight line. So the answer is going to be D. A slow vehicle and a fast vehicle travel towards each other in a straight line and then collide. Which outcome is never possible? Never possible. One is slow and the other one is fast. Both vehicles stop. I think that is possible. Both vehicles can stop. Only one vehicle stops. That is also possible. One vehicle may stop and the other one can move. The fast vehicle's speed increases. Of course, it must reduce. That one is not possible. The slow vehicle's speed increase. That is possible. The one which was moving slow, its speed may slightly increase, but the one which was moving faster, if it collides with another one which was moving slower, then its speed cannot be cannot be higher. So this is just common sense. So the answer is C. There is loss because during collision there is loss in kinetic energy. So since there is loss in kinetic energy, we expect that the one which was moving faster, its speed is going to be higher. I mean, it is going to be lower. So we can't expect its speed to increase, it decreases instead. But the one which was slower, its speed could slightly increase. In other words, it could be given more momentum by the one which was faster. So that is common sense. A football falls from the top of a tall building. Which graph best represents the way in which the distance x fallen varies with time t? A football falls from the top of a tall building. So this is distance against time. So distance must increase. Distance must increase. But remember, the graph of distance against time should give us the speed. A is showing that as distance increases, the gradient decreases so that a point reaches where velocity is 0. This one shows that velocity tends to 0. This is wrong. B is wrong because it is showing that velocity is constant throughout because it's a straight line, yet we expect there could be air resistance. This one is also wrong because it shows that velocity increases to infinity. The velocity increases to infinity. Remember the gradient? The gradient is going to be the speed. For distance time graph, the gradient is speed. If we expect that there should be air resistance, then the velocity should increase, but it should become constant with time. Terminal velocity is going to be reached. So I say this one was wrong because it shows that velocity tends to become 0 because the gradient becomes horizontal. This one was showing that velocity is constant, yet the velocity increases and then before it becomes constant. So here it is showing velocity increases and it then becomes constant. Of course, as the object falls, air resistance increases. There will be a point where the resultant force becomes 0, the acceleration becomes 0, so the velocity is constant. So the answer is D. The first part shows an increase in velocity up to somewhere, then it becomes a straight line here, which means the velocity is now constant. Here we have reached terminal velocity. So the answer is D. Two identical cars P and Q are traveling along a straight road. Car Q is traveling at twice the speed of car P. The brakes are applied to both cars, producing the same constant deceleration. The same constant deceleration. It is constant, so it must be a straight line. So we ignore B and D because these are not straight lines. It means the deceleration is not. Remember, acceleration is the gradient. Acceleration is equal to the gradient of a velocity time graph. So if it is constant deceleration, it must be a straight line. So constant deceleration must be a straight line. A straight line is the one which has a constant gradient, straight line. Okay. But they said the brakes are applied to both cars, producing the same. It is the same deceleration. So they should have the same gradient. Same deceleration means same gradient. So the lines should be parallel. Same gradient, which means the lines should be parallel. Should be parallel. It is parallel lines that have the same gradient. You notice that P and Q, the lines here are not parallel. So this is going to be out. So the answer is going to be C because C, we are seeing that the lines P and Q are parallel. As simple as that. A man stands in a lift that is accelerating vertically downwards as shown. Which statement describes the force exerted by the man on the floor? Of course, by Newton's third law, the force by the man on the floor should be equal to the force by the floor on the man. But the force, but this force could could be less than the weight. That's why the man is accelerating downwards. So I'm saying the force by the man on the floor is equal to the force by the floor on the man. That is if there was no acceleration, but the force, but that means the force by the floor on the man is actually less than his weight. That's why he is accelerating downwards. So I'm saying, but this force could be less than the weight. The force which the floor exerts on the man might be less than the weight. That is why the acceleration is downwards. That is why the acceleration is down. So the force by the floor on the man could be less than the weight. That's why the acceleration is downwards, because the other force acting is actually the weight. So it is equal to the weight. If it was equal to the weight, then there would be no acceleration. It is greater than the force exerted by the floor on the man. Of course, by Newton's third law, they should be equal. It is less than the force exerted by the floor on the man. By Newton's third law, they should be equal. It is less than the weight of the man. So the answer is D. Since the weight acts downwards and the man is accelerating downwards, it means the force by the man on the floor, which is equal to the force by the floor on the man, must be less than the weight. A snooker ball of mass 200 grams hits the cushion of a snooker table at right angles with a speed of 14 meters per second. The ball rebounds. This is very important. It rebounds with half of its initial speed. That means it rebounds with 7 meters per second. The ball is in contact with the cushion for 0.6 seconds. What is the average force exerted on the ball by the cushion? So by Newton's second law, force is equal to the rate of change of momentum. So the mass is 200 grams, which is 0.2 kilograms. The velocity changes from 14 minus negative 7. The negative is because of a rebound. Then divide by time, which is 0.6 seconds. So just take my calculator, 0.2 times 14 times plus 14 plus 7, that is 21. Divide by 0.6. So that is 7. So this is giving me 7 newtons. So the answer is B. Two railway tracks of masses m and 3m move towards each other in opposite directions. With speeds 2v and v respectively. These tracks collide and stick together. So they move with a common velocity, and their masses are combined. What is the speed of the tracks after the collision? So before collision, I'm conserving momentum. Total momentum before collision is going to be 3m times velocity of m, which is v. Because they were in opposite directions, one must be negative, so plus negative. The other one has mass m times velocity 2v. That is total momentum before collision should be equal to total momentum after collision. Since they stick together, total mass is going to be 4m times the common velocity, which I'm going to call vx. So I just want vx. So 3mv minus mv, that gives us only mv, equals to 4m times vx. M has cancelled, so vx is going to be equal to 1 over 4 times v. So that is a quarter v over 4. So the answer is A. A stone is projected horizontally in a vacuum and moves along the path shown. X is a point on the path. XV and XH vertical and horizontal lines represented through x. Xt is the tangent to the path at x, along which direction the forces act on the stone. If there is no air resistance, the only force acting is the force due to gravity. So it acts downwards, which is force due to gravity, acts downwards, vertically downwards, force due to gravity. So it only acts along xv. So it is xv. No, it is in a vacuum, no air resistance. The only force acting is the force due to gravity, which acts vertically downwards. So the answer is simply B. Only gravity acts. For projectile in a vacuum, only gravity acts. There's no any other force. The ball is thrown vertically upwards, air resistance is negligible, acceleration must be constant. Which statement is correct? Let's inspect the statement. By the principle of conservation of energy, total energy of the ball is constant throughout the motion. This statement is very correct, and I think this should be the answer. Total energy of the ball is constant, even though kinetic energy may be changed to other forms such as heat, but the total energy is conserved. By the principle of conservation of momentum, total momentum of the ball is constant throughout the motion. Now, total momentum of the ball is not constant because the ball alone is not an isolated system. Gravity acts on it. But if we talk about the ball and the earth, it will be now an isolated system. But the ball alone is not an isolated system because the force of gravity acts on it. There is a resultant force on the ball. That one is not conserved. The kinetic energy of the ball is greatest at the greatest height. At the greatest height, the velocity is zero, kinetic energy is zero, so it's not greatest. Potential energy of the ball increases at a constant rate during its ascent. When it is going upwards, potential energy of the ball increases at a constant rate. If air resistance is negligible, potential energy of the ball increases at a constant rate, not at all, because potential energy of the ball increases at a constant rate. Of course not, because the speed goes on decreasing, so it means it doesn't gain potential energy at the same rate as it goes higher, because it slows down as it is going higher. So this is also not correct. So the answer is A. A car of total mass 1560 kilograms is traveling with a constant speed of 32 meters per second. The driving force provided by the car is 680 newtons. The kinetic energy of the car is 800 kilojoules and its momentum is 50,000 newton seconds. Which two items of data could be used to calculate the useful power output of the car? Of course, we know that power is work done over time taken, which can be force times velocity. So let's check driving force and momentum. That does not give us power. Kinetic energy and mass, that one gives us momentum, not power. Mass and momentum does not give us power. Speed and driving force, so power can be speed. Power can be speed times force. An object has an initial velocity u and an acceleration a. The object moves in a straight line through a displacement s and falls and has final velocity v. The above quantities are related by that equation, v squared is equal to u squared plus as. Which condition must be satisfied in order for the equation to apply? Remember, every time we use this equation, the body is moving in a straight line and the acceleration must be constant. Every time you use the Stewart equations, because the acceleration is constant, that's why we call them equations of uniformly accelerated motion. So here, without wasting time, the answer is going to be C. The magnitude of acceleration is constant and the direction of acceleration is constant. The magnitude of A is constant and the direction of A is the same as the direction of V. So the answer is going to be C, the magnitude of the acceleration should be constant. Of course, for all of them, they are saying A is constant, A is constant. Here they are saying direction is of A is constant, and the direction of A is the same as the direction of S. The body does not need to accelerate in the same direction as the displacement. It does not need to have this acceleration in the same direction as the velocity, as long as the acceleration is constant. The direction of A is constant and the direction of A is the same as that. It doesn't need to be the same direction as you, as long as A is constant and its direction is constant. A car is traveling at a constant velocity. Its brakes are then applied, causing uniform deceleration. It is causing uniform deceleration. Which graph shows the variation with a distance s of the velocity v of the car? So, of course, note that v squared equals to u squared plus 2as. So since it is a uniform deceleration, these equations can work. It breaks, it means final velocity is 0. So I will say 0 squared equals to initial velocity squared minus 2as. Because it was breaking, the acceleration is negative. So it means u is going to be equal to the square root of 2as. So it means u is directly proportional to the square root of s. So that is not a straight line. So this one will not be a straight line, because it is u is directly proportional to the square root. If it was u directly proportional to s, it would be a straight line. But this is not straight. That will not be straight. So it means where we see straight lines, that is out. This is also out. This one is showing initially v is constant. That is not true. And then it decreases. Yet here it is showing that u, which graph shows the variation with the distance s of the velocity v of the car? So initial velocity is directly proportional to s. When u equals to 0, s should also be 0. When velocity is 0, s should also be 0. And when s increases, because there's a uniform deceleration, of course, if it is a uniform deceleration, as s increases, v must decrease. Anyway, for all of them, it is decreasing. So the answer is automatically going to be A. So it is a uniform deceleration. We see it is a smooth curve. So the answer is going to be A. It will not be a straight line. A ball is thrown across a flat field. Which statement describes the motion of the ball? Which statement describes the motion of the ball when the effects of air resistance are ignored? There is no air resistance. Acceleration is going to be constant. It means, remember, for projectile, velocity in the horizontal is always constant. If there is no air resistance, it is velocity in the vertical which increases. So the acceleration in the horizontal is 0. The acceleration in the vertical is g, and it remains constant. So the ball lands with the same velocity at which it is thrown. The horizontal component of acceleration is constant throughout the motion. The horizontal component of acceleration is constant throughout the motion. This is 0. The horizontal and vertical components of acceleration are both 0. This is not true. The horizontal and vertical components of velocity are both 0 at the highest point, not at all. It is only v in the vertical which goes to 0. The other remains constant. So it means the answer is going to be B. The horizontal component of acceleration is constant throughout the motion, and it is 0. So the answer is B. What defines force? Force is the rate of change of momentum. So I think the answer is going to be B. When a force acts on a body that is free to move, the force is the rate of change of momentum of the body. So the answer is B. force is the rate of change of momentum. A particle of mass m traveling with speed u collides with a stationary particle of mass m. The velocities of the two particles before and after the collision are shown. Okay. Which vector diagram represents the momenta? Momenta is plural, before and after the collision. Okay, so I'll just going to prolong this. So initial momentum is in this direction here. So this is the initial momentum. I'm going to transfer this vector here to this one. So without changing its direction, it will be like this. I think I've changed the direction. It's not very parallel. So I'm trying to draw a vector parallel to this one. And then the one in the horizontal. So this one, the momentum initially should be in that direction. The momentum for this one is going to be in this direction. So since it is in equilibrium, this should be forming the velocities of the particles before and after shown. Which vector diagram correctly shows the momentum before and after? Okay, before and after. So it means the answer is automatically going to be B. Before, it is mu. After, we have mu over 2 and mu3 without changing the direction. So the answer is, this is mu over 3. I just transferred this vector here to that point. This is initial momentum, mu in that direction. I just transferred this one. And this one is going to be mu over 2. So the answer is B. An object falls freely from rest in a vacuum, no air resistance. So acceleration is going to be constant. The graph shows the velocity variation with time of velocity. So remember, the gradient is the acceleration. Since it is in a vacuum, A is constant, so the gradient should be constant. So it means automatically, without wasting any much time, an object falls freely from rest in a vacuum. The graph shows the variation with the time t of the velocity of the object. Which graph using the same scales represents the object falling in air? Okay. So in air, it can't be like this. For in air, the gradient decreases. For in air, acceleration decreases. So it means the gradient must decrease. So this one is showing a constant gradient. This one is showing an increasing gradient. So that means it is wrong. This one is showing that the gradient just decreases. Here it is showing initial, it is falling in air, remember, but it is showing that there is no velocity for some time. I mean, there is no the velocity in there's a what? There's zero acceleration because here the gradient is zero here, so it is showing there's zero acceleration. Yet initially the acceleration would be 9.81. So there should be an acceleration, then it decreases. So the answer is C rather than B. Because here it is initial along the y-axis, which shows here it shows initial acceleration is 0. Initial gradient is 0. There's a change in v, but when there's no time. So it means it starts with 0 acceleration and again it decreases. So the answer is going to be C. There's some acceleration initially, but then it decreases to 0. A car accelerates uniformly from velocity u to velocity v. On the graph, which area equals the distance traveled by the car in a time t? So the distance is the area under the graph. So the area under the graph is going to be this one here. I want you to notice that this area here is the same as this one here. So let's see the options. NPTU, NPTU plus PQ, PQST, NPTQ, NPTU plus PTSQ. That is taking the whole area. That is not true. We must remove this part here. NPWV, NPWV plus VRSU. I think that is correct. NPWV, which is this one here, plus VRSU plus this area here. I think that is correct because when I take NPWV, I have left out this area here. It means I have not considered this area here. This is not considered. But when I add ARSUV, I've added this area here. So this area here compensates for this one which I have not considered. So it is the same thing. It is the same thing as having PTUN plus PTSP. So the answer is B. A student uses a spring. I think this is the last question for this part. A student uses a spring gun to launch a steel ball with a constant horizontal velocity. He varies the height h of the gun and measures the horizontal displacement r of the ball when it hits the ground. Which graph shows the variation with the height h of the horizontal displacement r? Okay, horizontal displacement r. Since he varies the height h, I'll use the simple equation S equals to UT plus a half AT squared. So since I'm finding the horizontal displacement, this part here is going to be for horizontal displacement, S or R is going to be simply U initial velocity times T. But then if I consider vertical motion to find the time, S is going to be H, is going to be, this was horizontal motion. So I'm considering vertical motion. H is going to be equal to initial velocity in the vertical is 0, so it is a half times g times t squared, meaning that t is going to be the square root of twice h divided by g, that is time. So it means the horizontal distance is going to be u, initial velocity, times the square root of twice h over g. So it means r is directly proportional to the root of h. That is not a straight line. So we ignore D. It can't be a straight line, so we ignore D. So when H is 0, R must be 0, so we ignore C. So for H equals to 0, R should be 0, so we ignore C. Then as H increases, R increases, but by finding the square root, you can use simple values such as if H is 0, of course R is 0. Let's say H was 4. It means R would be 2. Let's say H is 9. It means R would be 3. So you notice that H increases more rapidly than R, so the graph will be having a decreasing gradient rather than an increasing gradient. So this one is wrong. This one will be correct. This will be R is directly proportional to H squared. So the answer is going to be A. This will be a graph of R directly proportional to H squared. That is the one which has increasing gradient. But since R is directly proportional to the square root, that is a decreasing gradient. So the answer is A. I think that is the end of part. That should be the end of part 8. Let's start from here in part 9. Let's start part 9 from that point. I hope you learned something. Do not forget to subscribe, comment, anything that wasn't clear, I can try to give more light on it. Thank you, and until next time, bye bye.